so far we have defined what is complex exponential function. Now in this module we are going to further explore complex exponential function. Now we know that what is e raised to power z. If z is equal to x plus iota y, this is going to be equal to e raised to power x multiplied by cosine y plus iota sine y, or sometimes preferably we denote it by exp in parenthesis z. Okay, so that's our preference notation. Now in this definition we can see cosine y and sine y, where y is basically a real number. So we know the properties of these real valued functions, that is sine y and cosine y. One of the very important properties of these trigonometric functions involved in the definition of exponential function is that they are periodic functions. So they repeat their values after some specific interval of the variable. So for example, on the screen we can see the graph of sine x. Okay, so if we start from this point and we move like this, and when we reach at this point, then one cycle is completed, and after that the function will be repeating its value. Okay, so basically this number, this interval after which it start repeating the same values, okay, is basically 2 pi in the case of sine x. Okay, so after each 2 pi it will start repeating its value. Okay, so let's see the next cycle. Okay, so this is 2 pi now, and after this it will start repeating again. So after each 2 pi it will repeat its value. So in other words, we can say that sine of x plus 2n pi, where n is any integer. Okay, so if we are moving in this direction it is positive integer, and if we are moving in this direction then it is negative integer. So n is any integer, so the value of sine x plus 2n pi is going to be equal to sine x. So it is because the sine x is periodic function, and the similar observation hold for this other function cosine x, which is involved in the definition of exponential function, in fact complex exponential function. Now once again it is a periodic function, but of course there are different functions and their graph is different, but the period is same. In fact we can see that it starts from 1 and it goes on like this and like this, and after this 2 pi interval, once again it will start repeating its value. Okay, so you can see that this shape is kind of repeated again and again, so it's kind of a stamp. Okay, so this portion is kind of a stamp, and if you want to get the graph of cosine x for the entire interval of the real line, okay, then you just take this stamp again and again and again, and you get the graph of this cosine x. Okay, so in the next 2 pi interval it will start repeating its value, and up to so on. And similarly as the case of in the case of sine x, cosine of x plus 2n pi is going to be equal to cosine x. So it's a periodic function with period 2 pi, or mathematically precisely speaking, cosine of x plus 2n pi is equal to cosine x. Now we are going to use this information about these trigonometric functions to see what is going to be the consequences of these periods on exponential function. What behavior will this information will have on the exponential function. So remember, we know that if z is equal to x plus iota y, then exponential function is basically equal to e raised to power x cosine y plus iota sine y. Okay, now remember this is cosine x sine y, so these are periodic function. So in other words, we can just write them down as cosine of y plus 2 n pi, and this sine y can be written as sine of y plus 2 n pi. Okay, so formally, so we have this expression e raised to power x cosine of 2 n pi plus y plus iota sine of 2 n pi plus y. Okay, and in the next line we just write down okay, so the reverse part. Okay, so now in the expanded form, So we just compacted in the following form. So e raised to power x, e raised to power iota 2 and pi plus y. Okay. Now if we just separate this y from iota 2 and pi, then we get this expression. Okay. So this becomes, so this is just e raised to power z, and this is e raised to power iota and pi. Okay. So from this calculation, we can say that e raised to power z is equal to e raised to power z into e raised to power iota 2 and pi. Okay. So hence we have this property that e raised to power z plus iota 2 and pi is equal to e raised to power z for any integer n. Okay. So as a consequence, we have this property that e raised to power z is 1 if and only if z is equal to iota 2 and pi. Okay. And another consequence is that e raised to power z1 is equal to e raised to power z2 if and only if the difference between z1 and z2 is that of iota 2 and pi. So these are all consequences of this important observation. Now, what does this information affect when we are dealing with these complex exponential functions? If we have this number, for example, this is a complex number z1, and we map it to some number in the w plane. Okay, so this is the w plane, this is the z plane, and let's say this is the output of this exponential map. Okay, so this is e raised to power z. So this is basically the value e raised to power z1. So according to this property that if e raised to power z1 plus is equal to e raised to power z2, then this can only happen if the difference between z1 and z2 is iota 2 and pi. Now what does this information mean? Okay, so remember the real parts of z1 and z2 are equal. So there is no difference between the real parts of z1 and z2. So the only difference is that their complex parts differ by this number 2 and pi. Okay, so now we know that this is real axis, okay, and this is imaginary axis. Imaginary axis. So one thing is very clear, that this other number z2 is going to have the same real coordinate, or if this is, let's say, x coordinate, then it's going to have the same x coordinate. So for example, it's going to be on this line. Okay, so that's first observation. The second observation is it cannot be, z2 cannot be just any number on this line. So there is a constraint on the imaginary part as well. So what is the constraint? So the constraint is that the imaginary parts differ by this particular value 2 and pi. And for example, if n is equal to 1, then they differ by 2 pi. Okay, so this number is, let's say this number is alpha, and let's say this is alpha plus 2 pi. Then this z2 is going to be this number. Okay, so of course one output, okay, or one option is that z2 is this number. Okay, or it can be z alpha. Okay, so if this n is equal to 2, then it can be at a distance of 4 pi. Okay, so it can be this one as well. So for all of these z2s that differ with the z1 by 2 and pi, of course their imaginary parts differ by 2 and pi. So all of these are going to be mapped onto the same number. Okay, so similarly on the other direction. Okay, so if this is alpha minus 2 pi, then this is of course z2. Okay, so all of these numbers, so this z2 is mapped onto this number, this z2 is mapped onto this number, and this z2 is mapped onto this number. So the image of all of these numbers is going to be the same. Okay, so that's an important observation about complex exponential function. Let's try to explore further this phenomena in this particular case. Okay, so we have these complex numbers given in the following form: 3 by 2 plus iota, pi by 4 plus 2 and pi, and we want to see the images of these complex numbers under the complex exponential function. Okay, so what are these numbers? Okay, so in the z plane, let's see what are these numbers. Okay, so the real part, is 3 by 2. Okay, so let's say this is real part, which is 3 by 2, and the imaginary part is pi by 4. Okay, so let's say this is pi by 4, okay, plus 2 and pi. Okay, so these are not just this is not just one number, these are infinitely many numbers, and n is any integer. Okay, so if n is equal to 1, then if n is equal to 0, then this is going to be this one. Okay, so this is z0. If n is going to be 1, then it is going to be z1, and it will be at a distance of 2 pi from z0 along this line. Okay, so once again it is the same argument over here. So the real part is the same, but the imaginary parts differ by the value of 2 pi. So what is going to be where is going to be z1? So this is going to be z1, and the imaginary part of this z1 is going to be equal to pi by 4 plus 2 pi. And similarly on the other direction, so for example this thing, so this thing is going to be pi by 4 minus 2 pi, and of course this is basically z minus 1. Okay, so these are infinitely many points on this line. Okay, so let me highlight them again. So z1, z0, z minus 1, up to so on. So all of these infinitely many points, according to our previous observation, they are going to be mapped onto the same complex number under this complex exponential map. If we try to evaluate this value, this output, okay, so this is the input, and the output is going to be equal to 3.1 plus iota 3.1. Okay, so whenever we take a number, okay, so let's say this is the complex number. Okay, so let's just say this is 3 by 2 over here. Okay, so this is 3 by 2 over here, and pi by 4 is somewhere over there. Okay, so and then we have our z0 is somewhere over there. Okay, and z1 is going to be equal to at a distance of 2 pi. Okay, so you can see this is 0, this is pi, this is 2 pi, and so it is going to be z1 is going to be somewhere over here, and similarly z2 is going to be somewhere over there, and up to so on. We can move in any direction. So all of these points on this line, so they are going to be mapped onto the same point. Okay, so in fact we can see that the real part is going to be mapped to somewhere between 7 and 8. So it is going to be somewhere over there. So let's just say somewhere over there, and the angle of this is going to be equal to pi by 4, so it is 45 degrees. So this is basically the image of all of these numbers. Okay, so this is z2 mapped onto this under the exponential map, this z1 mapped onto the same point, this z0 mapped onto the same point. So all of these infinitely many numbers on this line, for which the real part is the same, but the imaginary parts are at a distance of 2 pi from the consecutive ones, all of these numbers are going to be mapped onto the same number. So this tells one of the important thing about complex exponential function, that it is not one-to-one function. Okay, we will explore this property further in our next module, but this is an important example which tells us about the behavior of exponential function. Now in this module we discuss a very important property of exponential function, that it is not one-to-one, and there is a kind of structure in the values, and we can easily say that for what values the output is going to be equal to the same number. Okay, so it is based on the observation that cosine x and sine x are periodic functions. So these periods of sine and cosine implies some sort of periodic structure to the output of these exponential functions.